Hi everyone, and welcome back to another episode of Science. In this episode I'm going to teach you how to build your own electromagnet and also some of the theory behind the electromagnet as to why it works. So if you want to build your own electromagnet, there's a few pieces of equipment that you need. The first one is a piece of iron. You probably don't have a piece of iron that looks like this lying around the house, but you may have a large iron nail. And if you don't have that and you really want to build it, you can always head to your local hardware store to pick up a piece of iron. At the moment, this piece of iron is not magnetic at all, but I will be turning it magnetic through the power of electricity. So stay tuned for that. You'll need some paper clips to have a play with, and you'll also need some wires. You'll also need a power supply. I'll show you what I'm using first. So I'm using a power box, okay, which allows me to control the voltage, and I'll be using the direct current ports, the DC ports. Now you probably don't have this power box lying around at home, so instead of the power box you can just use simple AA batteries. These are about 1.5 volts each. If you stick them together, you can combine them, so that'll be 3 volts, 4.5, and so on and so forth. You just need a bit of sticky tape to stick them together. So yeah, you can use batteries for your power supply in order to make your electromagnet work. But I'll use my power box just because it's a lot easier. Okay, so let's go through a little bit of theory before I go into building the actual electromagnet. There's two ways to make this piece of iron magnetic. At the moment, it's not magnetic at all. The first and most easy way I can make it magnetic is by connecting it to a permanent magnet. Now, there's a difference between the structure of these two pieces of iron. In this piece of iron, the atoms, or the domains, have all been lined up in one direction. And when you line up the domains of this piece of iron, when you line up the domains of a ferromagnetic substance, you can generate a magnetic field around the magnet. This piece of iron, though, the domains are not aligned. They're all scrambled up. The atoms are facing all different directions. The domains in this piece of iron have been locked into place. So we call this a permanent magnet or a hard iron. The domains in this piece of iron have not been locked into place. We call this a soft iron. Now, because the domains in this piece of iron are not locked into place, we can change their direction. And there's two ways we can change their direction. The first is by introducing a permanent magnet to it. The magnetic field of this magnet is going to align the domains of this soft iron. And so what I can do now is actually turn this one, the soft iron, into a magnet. So now I can pick up at least a couple of paper clips. But if I disconnect my permanent magnet, then they fall off. And once again, it's not magnetic. And that's because when I disconnect the permanent magnet, the domains inside of this soft iron scramble up again, and so it loses its magnetism. But when I connect the magnet, the permanent magnet aligns the domains of the soft iron, and it becomes magnetic again. And then once again, if I pull it away, it falls off. There's a second way to magnetize this soft iron, and that's through electricity. Now, it's not by running electricity through the iron itself, but around it. So you're probably wondering, how does that work? So I'll go through that next. The first piece of theory we have to understand is that when we run electricity through a wire, we generate a magnetic field that loops around the wire. Right, so I want to prove that to you first before I go any further. So I'll take my leads and I'll connect them to my DC power supply. And once again, you can do this with your batteries. I'll connect my wire to my alligator clips. Okay. Straighten out the wire, put the compass next to it. At the moment, the compass is aligning to Earth's magnetic field, but if I now switch on the power, you'll see the compass react and align to the magnetic field of the wire. Now I'll turn it off, and the compass goes back to the Earth's magnetic field. What's happening is, as I'm running the current, and it's right now running in this direction, I generate a magnetic field that's looping around the wire like this. And the compass is aligning itself to that magnetic field that's being generated around the wire. I'll now turn it on again, and you can see the compass react to that magnetic field being generated. Now if I change the direction of the current, right, so right now it's flowing in the direction of my thumb, and the field is looping around this way. If I change the direction of the current, so now I'll make it run this way. So now the current is running this way, following my thumb, and the field is looping around this way. Let's see how the needle reacts this time. This time it's the red side of the compass that's being attracted to the wire. If I change the direction once again, right now it's running that way. Let's see if the white side is attracted this time. It is. So depending on which way I'm running the wire determines which way the magnetic field is. And depending on which way the magnetic field is, determines which way the compass points. Now at the moment, the compass, the red needle is attracted to the south pole of the permanent magnet, and the white needle is attracted to the north magnetic pole of the magnet. When you are using your compass, and the compass is aligning itself to Earth's magnetic field, it's actually the red north needle that is aligning to Earth's south magnetic pole. Now, Earth's south magnetic pole is actually Earth's north geographic pole. So it's back to front. I'll say that again. Earth's north geographic pole is the south magnetic pole. And same way the other way. So Earth's south geographic pole is Earth's north magnetic pole. And that is how your compass is aligning. The red, which is the north magnet of the compass, is aligning to Earth's south magnetic pole, which in turn is Earth's north geographic pole. A little bit confusing, but you might be interested to know that. Okay, so now we know that when we run electricity through a wire, we generate a magnetic field that goes around it. Now we can use that magnetic field that is generated around the wire to align the domains of the soft iron. Let's do that now. Just give me a moment to disconnect the wire. I think I've got 10 turns on this coil at the moment. So I'll start with 10 turns. Organize my cables. So I'll have the negative end go this way and the positive end go this way. So I've looped my wire around my soft iron. Just fix this part, a little bit fiddly. When I turn on the electricity, the current is going to run through the wire and around the piece of iron. As the current runs through the wire, those magnetic fields are going to be generated around the wire. And those magnetic fields are going to align the domains of the soft iron. When the domains align in the soft iron, I will turn my piece of iron that is not magnetic at the moment, but I can make it magnetic once I turn on the electricity. So let's do that now. It can now pick up 3 paper clips at least, which is pretty cool. Now the power box does short circuit, so I can only turn it on for a limited amount of time. And using the batteries, it will drain the batteries fairly quickly. Now I can increase the power of my electromagnet through a couple of ways. I can first of all increase the number of turns. So if I go 11, 12, 13, 14, 15, 16, 17, 18, 19, can I fit 20th here? A bit tricky. So I've got about 19 or 20 loops or turns around my electromagnet. Let's see if I can pick up more than 3 paper clips this time. I'm keeping the volts the same. The volts have been on 4 volts for both. And this time I can pick up a few more. So increasing the number of turns also strengthens the electromagnet. And that's because you've got more turns of the wire, and therefore the piece of iron is getting more magnetic fields, stronger magnetic fields, to align its domains. So the more turns that you have, the more domains you are aligning in your electromagnet, and so therefore your electromagnet becomes stronger. I can also weaken or strengthen the electromagnet depending on how much voltage I'm using. So if I go down to 2 volts, I can only pick up 2, even though I've got 20 turns. I can try 6 volts, but I think it'll short circuit fairly quickly. So I'll turn it on. There we go, I can pick up heaps on 6 volts, and then the power box cuts out. But you can have a play of it on your own as well. This also is a good time for me to introduce the right-hand solenoid rule. Before, when I was talking about the single piece of wire, I was referring to the right-hand grip rule. When the current flows in one direction, your grip and the direction of your fingers show the direction of the magnetic field. That's the right-hand grip rule. For our electromagnet, we can also talk about the right-hand solenoid rule. Now the right-hand solenoid rule, your fingers this time indicate the current and your thumb indicates the north. So at the moment, my red lead is looping over my soft iron just here. So the current is flowing in this direction and looping over the soft iron. So I can wrap my hands around my electromagnet this way, because that's the direction the current is flowing. And therefore my thumb indicates the north end of this electromagnet. And we can test that out as well. If I bring the compass back, that's the north pole of the permanent magnet, and the white needle of the compass is attracted to the north magnetic pole of the magnet. If I turn on the electromagnet, let's turn it down to 4 volts again. I turn it on, and the north electromagnet is attracting the white needle of the compass. Okay, if that makes sense, then therefore the red side of the needle should be attracted to this end. And you can probably hear the power box cutting on and off. Might be able to make it work with 2 volts as well. Okay, the next step and what I can do is I can reverse the direction of the current. And if I can reverse the direction of the current, you can see the soft iron is still slightly magnetized and reacting to the compass. But if I can reverse the direction of the current and make it loop the other way, I should be able to change the poles on my electromagnet and therefore change the direction that these needles are facing. So if I change the direction of the current, I should be able to get this white needle to face this end and the red needle to face this end. So what I'll do is I'll just try changing the leads at the power box, swap their ends. Although, yes, that should work. So now the current is running through this one first, and this one is looping underneath the coil. It's looping underneath the coil. So in this case, I'm going to wrap my hand underneath, like so, and my thumb is going to indicate that the north end is on this side. And if that's the case, the white needle should now face this end. So I'll turn it on, and voila, the white side is now attracted to this end and the red should be attracted to that end. I'll flip it again. So now the red should face here, and now the white should face there. Beautiful. And that, in essence, is how you create an electromagnet and why an electromagnet works. I also went through two right-hand rules, the right-hand grip rule, when talking about a single piece of wire, and also the right-hand solenoid rule, where you can figure out which end of the electromagnet is the north end. Thank you for tuning in, and I'll see you on the next episode of Science.